In the last video, we saw an example of a function of two variables, and when we took the mixed second partials, we saw that they were equal. And I said that wasn't a coincidence, that was actually the result of Chloros Theorem, and there's Clairaut's name spelled out for you. Okay. And here's what it says. Given a function of two variables, a real valued function of two variables, if the two mixed partials are continuous on some open disk D. Now here I've emphasized the word open, and that's because in the statement of the theorem in your textbook they omitted that, and that's an error. It does need to be an open disk. I'll talk about the significance of that in a moment. But if these two mixed partials are continuous on some open disk D, then they're continuous on that disk D. Now, the significance of having an open disk is if I'm concerned about some point that's in that disk, I know that that point isn't on the boundary of the disk, because by definition, an open region doesn't include its boundary. Okay. Now, if this region is the region where these guys are continuous, now it's entirely possible that they're also continuous outside of this disk, but let's suppose they're not. Let's suppose that these functions fail to be continuous outside of the disk. I'm still okay at a point inside the disk, because I know they're continuous here, and I know that I can go away from that point in any direction. As long as I don't go too far, I'll still be within that disk, and I'll still have this condition satisfied. Okay. Compare that to if I had a closed disk. If I have a point on the boundary, and my mixed partials are not continuous outside of that disk. Now, again, this doesn't say that they're only continuous on the disk, but it allows for that possibility. If that were the case, my mixed partials would be continuous here, but if I went just a little ways away in certain directions that took me outside of the disk, they would cease to be continuous. So when you have an open region, whatever property is true at and near the point that you're concerned about. Whereas if you have a closed disk, it's possible that the property that you're concerned about is true at a point, but ceases to be true if you move away from that point. Okay, so we do require that we have an open disk. All right, some of you may be wondering, I hope you are, it happens most semesters that somebody wonders, does this apply in other cases? And there are two ways that we could modify the situation. One is that I could have a function of more than two variables. So if I have a function of three variables, are the mixed partials continuous? And the other way I could modify things is that I could look at higher order derivatives. So I could look at third partials or fourth partials. Now, even with a function of two variables, I can still look at mixed third partials, because I could simply take the partial derivative with respect to x twice and y once. And there are different orders that I could do that. I could go xxy, I could go xyx, or I could go yxx. Are those going to be equal? Well, the answer is yes, but we need to modify the hypothesis of this statement a little bit. The if part needs to be strengthened if we're working with either more variables or higher order derivatives. The generalization that works in all cases is that if all of the mixed partials of a certain order, so all the third partials or all the fourth partials, whatever one we're concerned with, if all the mixed partials of a certain order are continuous on an open region, if we're in three space, it wouldn't be an open disk, it would be an open sphere or some open region of three space. If we had a function of four variables, it would be an open region of four space. If all of the mixed partials of a certain order are continuous on an open region of the appropriate space, then any two of them that involve the same variables the same number of times will be equal. Okay. Now, there are certain scenarios where that much stronger condition can be loosened up just a little bit. But basically here, there are only two mixed second partials. But if I wanted to talk about third partials, we said there would be 8 of those. According to the theorem the condition that I just gave you, all 8 of those would have to be continuous in order for us to conclude that any 2 of them were equal. Okay. Now, as I said, there are some situations when we're working with relatively few variables or relatively low order derivatives where you can relax that condition a little bit. I'm honestly not sure exactly what they are. The application of Clairaut's theorem that we're going to need this semester and that you're responsible for is this one here. For a function of two variables, if the two mixed second partials are continuous on an open disk, then those two mixed second partials are equal. But I think it is interesting to know that, yes, that does generalize to functions of more variables and to higher order derivatives. All right. Now, what I'd like to do next is just take a look at what these second partials are actually measuring. And we'll take a look at it for a function of two variables, because that's where we can actually think graphically, because the graph is in 3 space. So if I had this, and let's say I wanted to take f sub xx, or the partial squared f with respect to x. And of course, if I'm calling the output z, I could replace the f's here with z's. More common to see it here than to see it here, but you can call the function f, or you can call it by the name of its output. Okay, if I'm looking at that, then both times I'm taking the derivative, I'm holding y constant. So I would be looking at a cross-sectional curve in a plane y equals y naught. That would be a plane that's parallel to the xz plane. Okay. So I'm looking at my cross-sectional curve. I take the partial with respect to x. That gives me the slope of the tangent line of that curve. I take the partial with respect to x of that. That actually gives me the second derivative of this curve. Okay. So a non-mixed second partial is actually a second derivative of a cross-sectional curve that you get in a plane like this that would be parallel to one of the coordinate planes. The mixed second partials are a little bit more interesting. Okay. If I were to look, let's say, at f sub xy, partial squared f, partial y, partial x. Again, noting that x gets written closest to f in both cases, but that means that reading left to right, it's not consistent. Okay, if I look at that, the problem is I'm not working with the same curve both times. Because when I take the partial with respect to x, I'm holding y constant. So I would be looking in a plane parallel to the xz plane. But then when I take the partial of that with respect to y, I'm holding x constant. So I'm looking at the graph of the partial of f with respect to x in a plane that would be parallel to the yz plane. So I'm looking in a different plane at a different cross section. Okay. So here's one way of thinking about that. I'm going to just work in 3 space, but without the standard orientation. Say here's x, here's y, and the z-axis is coming straight out towards us. Not the standard orientation, not what I'd use for drawing any graphs, but sometimes useful when explaining things when you've got a whiteboard handy. Okay, so when I'm taking a look at the partial with respect to x, I am holding y constant. So I'm looking in some plane that's parallel to the xy plane, and I'm calculating the slope of the tangent line. Okay. Now, the slope of a tangent line is, of course, a number. It's not a vector, but it does tell me the direction in which that tangent line is going. So just to be able to visualize, I'm going to say, let's suppose we were holding y constant at this height. Okay. And at this particular point, I determined that the tangent line then was going in this direction. Now I'm representing it visually here with this marker. Of course, it would actually be just a number. Okay. But then, when I take the partial derivative with respect to y, now I'm not looking at going left or right. I'm now looking at going up or down. So now we're saying, as I go up or down, how does that slope that I get change? Now, I'm sort of representing that here by just changing the direction in which my marker is pointing. Again, I do want to emphasize that these partial derivatives are numbers, not vectors. So when I'm using this marker, I'm just saying the number that I get for the first derivative is a slope, which tells me the direction in which the tangent line is going. Okay, but we're sort of looking at how this slope changes as I move up or down. So it's kind of an interesting thing to think about exactly what that is measuring.